Hello everyone and welcome to my mid-evaluation presentation on the project titled A Solar Collector for Domestic Steam Generation in Sri Lanka. I am N.A.N. and this project is supervised by Dr. J.C. Rajaguru. I'll be walking you through the progress I've made so far. Feasibility of this project. As a country located near the equator, Sri Lanka receives abundant sunlight throughout the year, and also the household energy demand is growing. As Sri Lanka has abundant sunlight, making it an ideal location for solar-based solutions. Solar energy could reduce reliance on fossil fuels, lowering both cost and carbon emissions. Yet, despite this, domestic solar steam generation is still underdeveloped in Sri Lanka, which is why this project is so crucial. During this first phase, I identified several knowledge gaps that needed to be addressed. The most suitable solar collector type for Sri Lanka was needed to be found first. The main consideration was this was not to an industrial scale but to a domestic scale. Optimal material selection for the selected collector type was also needed to be addressed. Heat loss minimization and then pressure and temperature challenges. There are several types of solar collectors that are available globally. First, I researched on several types of these solar collectors to identify the most suitable option for domestic steam generation. After analyzing features of these collectors and after discussing with my supervisor, I chose the parabolic trough collector as the most suitable option for this project. Here is why. They are high efficient for steam generation, cost effective for domestic usage, has both direct and indirect heating capabilities, and compatible with Sri Lanka's solar conditions. Parabolic trough collectors or PTC works by using a parabolic shaped mirror to concentrate sunlight onto a receiver tube. The mirror is designed to focus sunlight onto the tube along its focal line, which significantly increases the amount of solar energy absorbed. The receiver tube, typically filled with a heat-absorbing fluid, absorbs this concentrated sunlight, converting it into heat. The heated fluid can then be used for various applications such as generating steam or powering other thermal systems. Most of the operating systems use an intermediate oil to transfer the heat. This is indirect heating. In direct heating approach, water in the tube is directly heated by the sun. In indirect heating, water is heated in a heat exchanger to produce steam by using the previously heated oil. At this stage of the project, I am still exploring the most suitable heating approach. Both methods have their unique benefits and challenges, and my decision will be based on whether we can reach such higher pressures in direct heating systems. The main scope of my project is to improve the collector tube so as to absorb the most of the rays falls on it reflected by the emitter. To improve the performance of the collector with some innovative applications than the ordinary, I considered some factors like using higher conductive tube materials with a higher yield strength, using appropriate coatings, using appropriate liquids, and using evacuated tubes. When selecting a suitable material for collector tube, a material with higher thermal conductivity, durability, and ability to withstand higher temperatures and pressures should be considered. The mostly using copper tube for this has a better thermal conductivity but evaluated against the cost for domestic applications. Maximum pressure that a thin-walled metal tube can withstand can be calculated by this equation given. And when considering aluminium and stainless steel as two options, we can find that the stainless steel can withstand higher pressures. To increase the efficiency, selective absorber coatings are commonly applied on the surface of the absorber tube. These coatings are designed to maximize the solar absorptance while minimizing the thermal emission. Although there are various such coatings are used in industry, in domestic usage, cost-effective and easily available coatings should be used. Here are some such coatings I researched. Readily available activated carbon coatings were a great solution. Improving the absorbing quality of the fluid inside the collector tube can significantly enhance the efficiency of a thermal collector. This involves optimizing the fluid's properties to absorb, retain, and transfer heat effectively. Main fluids used in industry are synthetic oil, molten salts, water, and the new trend is using nanofluids. But here I researched on some innovative fluids with similar properties but easily available and cost-effective. According to the Sri Lankan Sustainable Energy Authority, we can get the data on solar irradiance of Sri Lanka. An area of 2 square meters can cover approximately a solar irradiance of 10 kilowatts per day. The dimensions are taken accordingly. The equation of the parabola is shown here. I have assumed a focal length of 0.4 meters here, and to be optimized, a rim angle larger than 60 degrees and lesser than 90 degrees is preferred. So a rim angle of 80 degrees is selected in modeling. One way of sizing the collector tube is optical error analysis. Collector optical efficiency is the ratio of solar energy falling on the surface of the absorber tube to that falls on the reflective surface of the emitter. To maximize this, the intercept factor should be maximized. Intercept factor is fraction of reflected radiation that is incident on absorbing surface of the receiver. This contains the effect of all the optical errors. The figure shows the solar intercept angle due to the sun width and image spread due to optical errors. One method for analyzing the effect and nature of optical error is treating all errors as independent random processes. Following is a graph showing the absorber diameter for various rim angles for 0.95 intercept factor using error analysis. While A1 represents the best case, A5 represents the worst case. By considering an error set of A4 for rim angle of 80 degrees, we can get the absorber diameter of around 50 mm. I did a solid modeling of the system by using SolidWorks. Here, the collector tube was my major consideration. I have modeled it by adding a high absorptive coating on the lower part of the surface and an insulation on the upper part. These features needed to be improved in future. Here are some challenges I faced so far. Material selection, efficiency improvement, steam pressure and safety, solar intensity variations, system scaling and practicality, cost constraints, lack of established benchmarks. And the future improvements of my project are improving the model, adding more suitable efficiency improving and innovative materials through literature survey, simulating the model validation. Here is the realistic time plan of my project. I did the project title selection and proposal presentation during the early phase of my project. Then I started the literature survey and feasibility study. My main consideration was on this part and still I am doing that task. Then I did the data collection and material selection part, and with the progress in literature survey and simulations, these phases may undergo changes in future. Now I am in the concept building and modeling phase. Here are the references I followed. That's all for now. Thank you so much.